Now, before we can discuss anything about the next state, black holes, we need to mention Einstein's general theory of relativity. Newton's law of gravitation is not enough to explain our universe. The gist of the theory is that mass curves the space around it, like a ball on a sheet. Imagine that we got the class together and we had a large sheet, and we were all around the edges and we were pulling it as tight as we could. Be nice and flat. If we threw a ball into the center, it's going to cause a dent no matter how hard we're pulling the sheet. And any other object that rolled by is going to fall into that curvature. So objects that are close to each other fall into the curved space. Einstein's theory predicted several things, including the gravitational deflection of light. So Einstein's general theory of relativity gave a mathematical and physical picture of black holes. Gravity is related to the curvature of space. A black hole is a place where the curvature of space is so extreme that a hole forms. The typical analogy is, imagine a waterbed with a heavier and heavier object placed on it. The analogy is only approximate, and a mathematical treatment is a little different. But his theory predicted things like the bending of light. And so if light comes very close to, say, our sun, and we have the sun here, and a gravity well of the sun is pretty steep. So during an eclipse, when the sun is not blocking out, we look at a star, and a star may appear to be right here. Its real position could be behind the sun, and the light is curving around, and we see it from Earth, so that stars appear to be in different locations when we're looking close to the sun. In 1919, British astronomer Arthur Eddington used the eclipse of the sun to test this theory. During the eclipse, the stars that were then visible around the sun were actually in different positions in the sky than when that section of the sky was seen 6 months earlier, thus giving validation to Einstein's new theory. So back to the death of stars. Above about 3 solar masses, even neutron stars are unstable. The gravitational force is so strong that no physical force can halt the collapse. Remember, the closer the objects are, the stronger the force. It seems that eventually we get infinite density and zero volume. This is called a singularity. The question is that a paradox? Can you have infinite density? Can you have all the mass of a star in zero size? Well, it may be a problem, but we can never see it. Nature protects itself. They say it puts a band-aid around itself, because a black hole is formed around the singularity, preventing us from ever seeing it. A black hole is a region of space from which light and matter cannot escape, but they can enter it. We can understand this in terms of the idea of escape velocity. We know the stronger the gravitational field around an object, such as a planet, the higher the escape velocity. In a black hole, the gravity is so strong that the escape velocity is greater than the speed of light. The physics of this is actually somewhat more complicated. To understand it properly, you would need to understand Einstein's general theory of relativity. Now, Einstein's theory also predicts strange behavior near a black hole, such as clocks run at different speeds depending on the strength of the gravitational field. In fact, a very accurate clock, if I had 2 clocks, one at sea level, one, let's say, in Colorado, they're actually going to run at slightly different rates. It's not that one's calibrated wrong, it's just that time moves differently depending on your gravitational field. It's something we can actually measure now. If the sun were to collapse to form a black hole, which it cannot do, it would be a few kilometers across. The Earth, if it collapsed down, would be a centimeter across. But our motion around the sun would not be affected. At large distances from the sun, Newton's laws would still apply. So if we can never get any light from it, how can we detect a black hole? There are probably many black holes in the galaxy, but because they're so dark, we can only detect them if they're in a binary system. The star Cygnus X1 is a prototype of such a star. There is a visible star whose Doppler shifts indicate that it is one of a pair of binary stars. The other is invisible, but has a mass too high to be a white dwarf or neutron star. Also, the companion is too faint to be a main sequence or giant star. So, by process of elimination, it can only be a black hole. The corroborative piece of information is that Cygnus X1 system gives off very powerful X-rays. X-rays are a sign of gas at temperatures of millions of degrees from Wien's law. The likeliest way of producing this emission is an accretion disk around a black hole. So in this binary star system with a black hole that we can't see, as material comes off of the binary star, some of it gets down and it goes into orbit around the black hole, and collisions cause it to slowly spiral in. As it spirals in, it's going faster and faster, its temperature is hotter and hotter, and finally, just before it falls in, some of it gets shot out in jets along the poles of the spin of the black hole, and we see a strong X-ray source as the material falls in. So the black hole is so close to the other star, it sucks gas off it. The gas is rotating as it falls in and goes into a disk where it heats up as it falls into the black hole. It is a paradox that while black holes themselves are infinitely dark, they can indirectly produce an enormous amount of power. Black holes are also found in the nuclei of distant galaxies and may be responsible for the most powerful objects in the universe, quasars. What I'd like you to do at this point is stop watching the video and watch the black holes video, which will give you a much better understanding and a lot better graphics on how black holes work and the science behind them and all the different strange things that are going around them. It's a pretty good video. I think you'll enjoy it.